Ready to get started. And we ended up yesterday with this sort of brief introduction that gave you a little bit the context of how fire safety is relevant to aspects such as building design, for example. And I highlighted a number of different problems that start becoming quite clear. It becomes quite clear that there are problems that relate to combustion. And so what I'm going to try today is I'm going to try to set up the problem in some level of complexity, and then bring you back, to the extreme level of simplification that today is used for purposes of design. Okay? So we're going to start by putting all the complexity and then recovering it all back until we come up with something that is tractable and that can be resolved using very, very simple tools. But in the pathway of doing this sort of back and forth, we're going to highlight a number of different issues that need to be addressed and need to be understood in an appropriate way. So the relevant part of fire safety that pertains combustion, normally we call it fire dynamics, and tends to be all the physical processes that accompany a flame, and in the context of fire safety. Now, as we addressed in lecture 1, fire is much broader than combustion. We're talking about building structures, we're talking about architectural design, we're talking about numerous technologies that could come from areas like electrical engineering and so forth. So fire engineers interact quite extensively with a broad range of disciplines, and I hope that through the introduction that I made yesterday, I made that quite clear, that it is a profession where combustion plays a very significant role, but combustion is actually a narrow aspect of the problem. But it is also a very, very fundamental part of the problem, because it almost sets the boundary condition for everything else. Okay? So without a real proper understanding of combustion processes, it's very difficult to evaluate the performance of any system that pertains fire, whether it is a lithium-ion battery, a forest fire, a smoke detector, photovoltaic cells. It doesn't really matter what the system is. To be able to assess performance, we need to have a fundamental understanding of combustion. Now, society, as you can tell from the image that I chose as background, requires a lot from us. And among the things that society requires from us is concepts like, these sort of live facade systems that, as you can tell, these are trees, and trees have properties of burning. So again, you're introducing combustible materials in the building envelope. So contextualizing combustion in the broader space of fire safety is necessary to use the knowledge in a competent way. And I emphasize the concept of competency, and why right now, we are living a period in which competency to some extent has been lost, and people are using these tools in a very poor manner. Okay? So that's where we ended up yesterday. And so as I say, today I'm going to enter a slightly different space, which is a little bit more technical, but as I say, with the idea of bringing you all the way to a solution. Now, once we have the solution, as simplified as it is, then tomorrow we'll break it back into components and look in more detail to certain components, where the uncertainties are, and how these oversimplified systems can be actually constructed, by using a combination of theory, data, computations, and so forth. So first thing that needs to be addressed is that in fire problems, the issue is generally an issue of time. It's a race against the clock. Okay? So when we are talking about performance of any system pertaining fire, we are going to inevitably have to use time. Okay? Now, time can be used in a number of different ways. So, for example, there is going to be the time that it will take you to evacuate. So, for example, that is a real, tangible evaluation of a process of people removing themselves, from a space. So if you think about it, if a fire was to start in this room, that fire is going to start growing, and there you have a characteristic time. And that characteristic time is going to give you the rate at which the fire grows. Now, at the same time, the fire is producing smoke, and that smoke is filling up the room. And because it's buoyant, it's first going to go to the top, but at some point it's going to descend and effectively start interacting with people. And there you have a second characteristic time. Okay? Now, then you have, as I say, your egress time. So in this process by which the fire is growing and the room is filling itself up with smoke, people are going to be moving around the building and trying to get out of areas of risk. And that, again, is yet another time. Okay? And eventually, as the smoke descends, it restrains the amount of air that can get towards the flames, and basically the smoke starts increasing in temperature because it has to heat up less and less and less air that is coming in, and eventually your smoke is so hot that it's going to start radiating sufficiently to all the combustible materials, and you can get ignition in a generalized way of all combustible materials, and that's what we call flashover. There you have another time. And these times keep occurring, and at the end, the purpose of trying to understand the fire is to be able to predict its evolution, within a space as a function of time. Okay? Now, I'm going to set up aside one of the times, and I'm not going to really touch it in great detail, and that's the evacuation time. So the evacuation time I'm calling TE, and generally your objective is that that evacuation time has to be much, much smaller than the time that it takes for the fire to reach conditions that we can label as untenable. So what are conditions are untenable? Conditions are harmful, to the individual. Now, why do we put a much, 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 much smaller? Is because do you think that you as individual people are predictable? No. So the uncertainty of any egress time is going to be massive, okay? So if this number here has a very, very large error bar, the only way I can have certainty that people are going to be able to evacuate with a certain level of safety is by making this number extraordinarily big. Is that okay? So in terms of this one has to be much, much greater than this, so that this number covers the large error bars associated to the uncertainty of human behavior. Okay? So this we normally call the R set and the A set. What is the R set? The required safe egress time. Is what time does it take to get everybody out safely? That's your required time. And this one has very large error bars. The A set is the available safe egress time, which is the time that it takes for the space in which people are to start creating conditions that are harmful to the individual. Is that okay? So a very straightforward concept. Now, in parallel, you're going to have other times. So, for example, your evacuation time has to also be much, much smaller than what I'm calling TS, which is your structural time. So what is the structural time? The structure starts heating up. And as it heats up, it is going to be damaged. And eventually, it's going to lose its functionality. So the moment it starts losing its functionality, you have reached a failure condition, and that is your structural time. Now, again, you don't want the building to start losing its functional value when people are still in there. So the error bar, again, is very big, and therefore, once again, we have much, 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 much smaller. Is that okay? So your safety factor has to be very big, given the massive uncertainty of the egress time. Is that okay? So in many cases, particularly when you have complex buildings, if I'm going to build a very tall building, or I'm going to build a building in a very densely populated area, or if I'm building a power plant, or I'm building some critical infrastructure, any of those cases where I'm going to have a structure that can have the potential of creating massive damage, then I would like my structural time actually not to be only much, much bigger than the egress time, but actually I would like it to be infinity. In other words, I'm designing for burnout. What basically means is that all the fuel will be consumed and the structure will still fulfill its functionality. Is that okay? So tall buildings is a perfect example of structures that are designed for TS 10 to infinity, which is the design for burnout. In other words, the structure will never fail. Okay, that's the objective. And by doing so, you've guaranteed that it's much greater than the egress time. Now, many times architects ask me, how do I identify a good fire engineer? And the answer is always a very difficult answer. I never know really exactly what I say. But I always say that it's much, much easier to identify a bad one. Okay? So if anybody, for example, tells me that my time to reach untenable conditions is 2 minutes and 52 seconds, okay? And my time to evacuate people is 2 minutes and 47 seconds, and therefore is okay. What does that mean? That's a very bad fire engineer, okay? Because they're not taking into account the error bars. Is that okay? And it is the same thing with the structure. Many times people think that when we're talking about a structure to be fire resistant to 2 hours, to 3 hours, what they think is that the reason for those 2 hours is to allow this evacuation to happen. And it is not the case. In most of these cases, when you're talking about 2 hours, that 2 hours is a representation of the time to total fuel consumption. Okay? So what it means is that it will take 2 hours for the total burnout of the fuel. Okay? That's what it actually means. And it doesn't mean that 2 hours is the time for evacuation. Is that okay? So those are symptoms that you get of somebody that really doesn't truly understand the problem. So this become the objectives, sort of the general objectives of the fire safety strategy and the things that we need to demonstrate. And as you can see, they're all expressed in terms of time, okay? So the first time, as I say, the required safe egress time, basically is establishing how long does it take to get people out, and I'm not gonna touch that at all, okay? So let's just leave it there. There's millions of ways of doing that, but in essence, what it is an empirical formulation, okay? What is an empirical formulation? People have been, for decades, collecting data, okay? So that data is basically they do tests, and they see how long people take to get out. They measure the velocities of displacement. They measure them according to, for example, people density. So if you have a room like this that has the capacity for 150 people and you only have 30-something people in the room, your density is very low, so people will displace themselves freely, but they will not displace themselves in an organized way because they're not packed. Well, if I increase the density a little bit more, then you optimize the speed because we start behaving like cattle. You know, if you have a cow that walks, then the other cow walks behind and the other one walks behind and everybody orders itself, and then you get this sort of optimal behavior where everybody's moving at an optimal speed. Now, if you put them too dense, then they start interacting with each other in a negative way, and the result is that the speed starts slowing down incredibly. Now, there's a beautiful experiment. You can actually see it in YouTube. You know, there's a whole bunch of videos of that. It's basically, imagine 6 people, okay? Some men, some women wearing heels, you know, others with flat shoes, and different heights, okay? And they're all holding a broomstick, okay? And you separate them a certain distance, and you have them all holding the broomstick. Okay? And then you ask them to walk. And you can see how nicely they walk. They walk freely because they're sufficiently separated. And then you change the condition, and you ask them now to get much closer so that their arms are bent. Okay? And they hold the broom, and then you ask them to walk at the same speed. In no more than 3 steps, one has tripped, and they all fall down. Okay? Now, it is really interesting how we have evolved in a cognitive way. And the critical distance is your arm's length. So anything that is within your arm's length distance is going to intrude into your own personal space and your own natural displacement. So the moment you are closer than your arm's length, you start interacting with the person that is next to you. If anybody is further than your arm's length, you are operating almost in an independent way, and then you can actually move in a very smooth way and absorb any variances between the different people. So that's that concept of bringing people too tight is choking. It's the same thing as fluid mechanics when you have choking flow. It's exactly the same thing. People get stuck, they start tripping on each other, and the flow stops to a halt instantaneously. Okay? So we need to understand all these things to be able to calculate those times. But as I say, they're always somehow estimates. Okay? And why they're just estimates? Because one, human behavior can vary in a very, very, very broad range. But also, any test that you can conduct on emergency evacuation is not going to be real. Okay? The only data that we have that is real is CCTV camera data that has been taken in real events. But the majority of the data that we use is data that has been constructed in an artificial way, so you're not really behaving exactly the way you will behave in the event of a fire. Okay? But nevertheless, we construct these estimates, and they give us this required safe egress time. Okay? So now let's talk about the ASET. Okay? And let's first, before we get into it, think about the problem. So I'm going to go very old-fashioned here, and I'm going to use the blackboard. And I was told that lighting control. Let's do it. Anyway, I'll just use the blackboard, but that light doesn't seem to come back again. I'll try once more, make sure. It says all on, all on. Okay, it doesn't do it. Anyway, please let me know if you don't see it, okay? But let's think of the problem. Now, time is the issue, okay? Here I have a room. Very simple, one opening, okay? And I'm going to put some furniture in it. Okay? And I'm going to start the fire. Okay, let's think about it. What are the things that I need to consider? Sorry? Yeah, no, let's take the people out, because they say the A set, we put it on the side. Sorry, the R set, we put it on the side. Let's just focus only on the fire, because I need to compare the two of them, no? Okay, so let's just focus on the fire. So once you know how many people they are, you can estimate what your TE is going to be. Okay, so let's say we've done that. Okay, we know it's going to be a certain value, you know, with a massive error bar. Okay, but we know that. Now, let's focus now on the other one, the TF. Okay? And how are we going to, what do we need to consider to be able to understand this TF? Sorry, size of what? Of the room. So effectively, you're going to have a room, less conventional heights, floor to ceiling height, about 3 meters. Normally, if you take a very, very conventional hotel room, you will probably have 6 meters, you know, by 6 meters. Okay, very straightforward. Yeah. Yes. You go first, you go next. Okay, so you're going to have the mass of fuel as a total mass of fuel. Is that okay? So this is basically kilograms. Are we okay? Yes. Well, let's just get to the opening factor when we get to the opening factor. What is the meaning of an opening factor? So basically, it is the capability of ventilation. So you're going to have a door. In this case, I'll just put one. And to see how much air is going to get in other words, the oxidizer that is getting into the room, I'm going to have, let's say, dimensions, 2 meters. I'll make it very small just to round it off, 1 meter. Okay, so that's my door. That gives me the ventilation. And so the size of the door pertains ventilation. Is that okay? What else? Okay, so we need to understand where the fire is going to start. Can we figure that out a priori? How? The fact that you have an outlet doesn't mean the fire is going to start in the outlet, because it could start where in the appliance that you plug to that outlet. Yeah, so basically, if you're going to start a fire, you're going to have a source, and you're going to have fuel around it, okay? So somewhere in this room, okay, there is going to be fuel around it, and there's going to be an ignition source. So you have to consider ignition sources. Okay? And of course, the relationship between where are the potential sources of ignition and any kind of combustible materials is something that you will have to consider. Okay? But there you, again, you have a pretty big error bar, no? Is that okay? Because, I mean, it doesn't really matter. I mean, I could put my computer in that bag in there, in that sofa, and that becomes a fire source. Is that okay? Or I can leave it there, and all of a sudden I move it, despite the fact that my plug is actually here. Okay? So things can significantly vary, so the ignition source becomes a little bit problematic. Okay? Already a little bit of a problem. Now, what else do I need to consider? Yeah. Okay, so you need to have all the properties, no? And the properties are not only going to be of the compartment, so you're going to have properties, and those properties pertain a number of different items: the fuel, the walls, the linings, etc. Is that okay? And you need to know all this, yeah. Yeah, it's covered in the properties, no? Anything else? Okay, so you need to include also the things that you put in there, like sprinklers, for example, water suppression. So if I decide to put a sprinkler, that sprinkler is going to affect the behavior of the fire. Okay, and I need to consider whether that is, what kind of effect that is going to have in the fire, no? So there's a suppression. I mean, obviously I have to consider detection and alarm too, but the detection and alarm does not affect the fire itself. Okay, is going to affect my evacuation time. Is that okay? What else do I need to consider? Yes? So basically I put a single door of these dimensions. Would that be enough? So would it be different, for example, if this door was a window? Yeah, because if you have wind, your boundary condition is changing, no? So in essence, what you're saying is that when talking about ventilation, it's not only the size of the opening, but it's actually the nature of the boundary condition, no? Is that okay? And all those things are relevant. What else? Yep. Okay, so basically you're going to have, among the properties, you're going to have the fuel, but you also have to consider the air. No? Yep. Oh, that's correct, no? So again, it will be the boundary condition, no? So if I put a ceiling fan, I'm going to create motion of the air, and that's going to have an impact. So the boundary condition needs to be considered very carefully in all its forms. Okay? That's it? Okay, so let's assume we put all the list of more or less things that we're looking for. Now let's try to evaluate things in terms of time. Okay? Let me create a scenario. Okay? And my scenario starts the problem with simply a short circuit. Okay? That's your ignition source. Okay, so what happens when you have a short circuit? Yeah, so basically what you get is two electrical cables effectively touch with a minimum level of resistance, which creates a high amperage, through the system that effectively releases an enormous amount of energy and potentially can result in sparks and hot material going in all directions. They don't necessarily have to touch, because if you put them too close, they can arc. So you can actually have a plasma that gets in there, and that serves as ignition. Okay? Now, will a short circuit have enough temperature to ignite a chair?
If it goes long enough, yeah.
Oh, well, no, you just added another variable. I just asked temperature. Let's get to the long enough. Okay? But first it's temperature.
When the circuit first closes, the temperature is at ambient.
Yes? And then what happens?
Well, you have I squared T,
Yep.
which builds up your temperature, and presumably the fuse doesn't pop, the circuit breaker doesn't pop.
Well, the potential that it doesn't pop exists. But how does it look, the temperature evolution, T as a function of time of a short circuit? It's going to start at ambient, as you say.
It'll start linear.
Okay?
It'll asymptotically get to a value where the temperature with a heat loss on convection radiation
Yep.
equals the heat input
Yeah.
I squared R.
Yeah, but how high would that be? Give me a sense. It's going to be 100, 400, 1,000, 1,500?
With a good copper conductor, I would guess only a few hundred in the conductor, but in the contacts,
Huh, that's what normally happens. So it's false contacts, yeah.
you can have several hundred. You can go into 1,000 feet.
Yeah, so let's say you go up, and then as you say, it reaches equilibrium, and eventually the fuse goes off or something happens, and eventually this dies, okay? But this can be on the thousands of Kelvin. Is that okay? And what is the time of this peak? Milliseconds, no? So it's going to be a very, very short period of time. So let's say this is of the order of milliseconds. Okay, here's my heating profile. Can I ignite that chair? Yeah, you have all these properties. You have a chair, it's polyurethane covered by cotton fabric with a plastic backing and a structure made out of metal with the tablets made out of wood. If I have a profile that gets to the thousands in milliseconds, can I actually ignite that? How would you assess that? But why? I mean, you know, I have the heating profile. Can I estimate heat transfer coefficients, radiative heat transfer? Can I make all the calculations? Let's make all the calculations. So effectively, you're going to do a calculation that takes this, you know, through heat transfer, okay, to my chair. Is that okay? So what is the condition that I need to verify to make sure that that chair ignites?
I would say its response to a pulse of energy.
I'm giving it the pulse of energy. You have the profile there. So what is the ignition condition I need to be able to verify on the chair? Huh? No, the material properties, I have them all. Yeah, but what is ignition of the chair? What is the ignition condition? What has to happen physically for that chair to ignite? Okay, so you're now using the right terminology. But let's start with defining all these things. So you're doing heat transfer. So effectively, the chair is going to start heating up. Is that okay? So it's going to increase in temperature. Okay, and because of its constitution and its properties, the surface is going to heat up faster, and you're going to have a gradient of temperature in depth. Is that okay? So you can actually do the heat transfer, and let's say, given the heating profile and having myself all the coefficients, okay, which already is a bit of a problem, I might be able to get the evolution of the temperature in time and in X, Y, Z of the chair. Is that okay? Huh?
So far, so good.
Yep. Okay, so then what is then the threshold? You said you mentioned pyrolysis. Okay, so what is pyrolysis in itself?
Breakdown of the material and the evolution of gases.
Okay, so basically what you're doing is you're providing heat to the point where the material, the chemical composition of the material starts breaking down into smaller molecules. It's an irreversible process by which bigger molecules become smaller molecules, and they move from the condensed phase to the gas phase. Is that okay? So that normally will follow an Arrhenius type reaction. Okay, so I'm going to have some sort of reaction rate. Okay, and that reaction rate is proportional to some sort of exponential e to the minus RT. Okay, and there's going to be some sort of critical temperature here that eventually produces enough fuel per unit area and per unit time to create a combustible mixture. Is that okay? So in essence, now I have a combustible mixture. Are we happy with that? So now I'm pyrolyzing, okay, and I'm producing fuel. Now, what has to happen before it ignites?
You have to mix the fuel and the oxidizer.
Okay, so then there's going to be mixing. Hold on, let's go step by step. So now you're mixing the fuel and the oxidizer. Okay, so now you have the two of them there. And now I have to increase the temperature, no? Okay, and I have to increase the temperature again until some other reaction rate now is not pyrolysis, but now it is combustion, okay, which again is proportional to some sort of minus E over RT with another critical temperature, And eventually you get a reaction that is producing sufficient energy to compensate for the losses, and as a result, you get a flash. That's what we call the flash point, okay? A flammable mixture that reaches a condition in which it can ignite and it can burn, okay? Now, why we call it a flash point? Because by itself it's not sufficient. Because once I've burned the flammable mixture, my ignition source is gone. What needs to happen? How does it become self-sustained? Yes? Yeah, so basically, your reaction rate of combustion has to sustain your reaction rate of pyrolysis. Is that okay? So this we normally reflect in terms of what we call the mass transfer number. Have you heard the B number? Droplet combustion. The gasification of a droplet is controlled by a ratio of how much heat is coming in as opposed to how much heat do you need to gasify it. So in the numerator, you're going to have the energy to heat the air, the energy to heat the solid, and in the denominator, you have the heat of pyrolysis. That ratio is the mass transfer number. Is that okay? If the mass transfer number is greater than 1, it basically extinguishes. If it's smaller than 1, sorry, the opposite. If it's greater than 1, it burns, and if it's smaller than 1, it extinguishes. Is that okay? Because you don't have enough energy. So effectively now you're dealing with chemical kinetics, both in the solid phase and in the gas phase, and the relationship between those two chemical kinetics. But the result of this is that now I have fuel being produced in a sustained way. Is that okay? So now I have my little flame. Now what needs to happen next for the fire to grow? Huh? Yeah, and what has to happen for fire to spread? Okay, so let's say you started with your chair and it ignited in this point, and then heat now has to be provided, a heat flux, so that the fire starts growing. In other words, its area increases as a function of time. That implies, again, heat transfer now from the flame that is in here to the solid, not to pyrolyze, but to bring the temperature up so that pyrolysis can start. In other words, I go back to here. Is that okay? Are we happy with that? Now, what forms of heat transfer do you need to consider? Conduction, convection, and radiation, all three. You're going to have conduction through the solid. You're going to have convection, many times is a heat loss, and you're going to have the flame radiating. Okay? Now, characteristic timescales. Are they consistent? Radiation, convection, and conduction, which one is the slowest? Conduction, particularly in this type of materials, porous media, very low thermal conductivity, very, very slow. So I'm going to have three characteristic timescales: convection, radiation, and conduction. Okay? And those three characteristic timescales are completely inconsistent with each other, because radiation is dominated by the speed of light. Is that okay? So its characteristic time is proportional to the inverse of the speed of light, very small. Okay? So TR, or tau R, is much, much smaller than T convection, which is much, much smaller than T conduction. So if I was to model this numerically, who determines my time step? So who defines the characteristic time step of a CFD code that has to resolve heat transfer from the gas phase to the solid phase? I'm talking about the time step. Okay? The conduction being the longest is the duration of your computation. Is that okay? But your time step is defined by the shortest characteristic time scale because you have to be able to resolve how things change as you increase the radiative heat transfer. Is that okay? So here I have a problem of completely dissimilar characteristic timescales. Now, in the meantime, what am I doing? This flame is producing smoke. Okay? Products of combustion that are now accumulating at the top of my compartment. So I have smoke now at the top of the compartment. Okay? Now, the transfer of smoke up is going to be consistent with which timescales? The convection, because it's fundamentally the same. So I have another process that, again, is dominated by the convective timescale, okay? Somewhere in the middle. Now, what is that smoke going to start doing to the compartment? Yep. Well, it's going to radiate heat, but is it going to radiate when what happens? The temperature goes up, and what else? Yeah, but for the smoke to be able to transfer heat, radiate heat, as he said, what do I need in the smoke? Huh? Particles, okay? Because if the smoke does not have particles, what you're going to get is purely gas emission, okay? And the temperature that you will have to go if only you are emitting in the CO2 and the CO and the H2O bands is going to be much, much higher for the same amount of radiation that if you have soot particles, okay? So as the smoke starts producing soot particles, then I actually start increasing the radiation. So all of a sudden now I have this characteristic timescale, but now I need soot, okay? And I need the temperature of the smoke. Is that okay? Now, to be able to get the soot, what do I need to be able then to resolve? If I want to know what my soot volume fraction is going to be, what do I have to resolve in this problem?
The degree of completeness of the combustion reaction.
Absolutely. So basically, I have to be able to resolve the chemical kinetics. Is that okay? And then you have a characteristic timescale of the chemistry. Is this time bigger or smaller than this one, or this one? Where does it fall? It's between radiation and convection. No? So this one here actually falls somewhere in here. No? Is that okay? And I still need to resolve that. Now, for that chemical kinetics to be able to be resolved, do I need the temperature of the flame? To be able to resolve the chemistry that leads to the production of soot, do I need to know the flame temperature? Yes, and the flame temperature is dominated by what? Is the air that comes in, so now you have entrainment. So you need to be able to resolve the fluid mechanics that leads to a characteristic buoyant velocity. That gives you the supply. But that supply is being altered by your door because you have friction. Okay? Needless to say, it's altered by your fan because you are creating turbulence. Is that okay? So all of a sudden now I need to be able to calculate this buoyant flow to understand what the air entrainment is going to be. And this buoyant flow is going to have a characteristic timescale. Where is it going to fall?
Probably be
Yes, because now the scale is bigger, no? So this velocity is higher than what is happening very close to the surface, where the flow is relaminarizing itself and you have very low velocities. So probably this TB is going to be somewhere around here. Is that okay? Are we all happy with that? So now I have entrainment producing with its interactions with the flame is going to produce smoke. The smoke is going to be at a certain temperature with a soot volume fraction that is going to dominate the radiative heat transfer from the smoke to the surfaces. The compartment surfaces are going to introduce friction, which is going to affect the characteristics of the buoyant flow. And the characteristic length scale could be the flame, but it could also be the compartment, because if the flame becomes very big, then it's the height of the compartment that limits it. Now, can I separate the boundary conditions from the fire itself to be able to resolve this problem correctly? Could I actually solve 1 cubic millimeter of this and then use that information to extrapolate the solution of the rest, ignoring the existence of the boundary conditions? I can't, no? So in essence, the characteristic length scale of the problem is always the characteristic length scale of the room. And this becomes my computational domain. Okay? So this is my LR. Okay? Now, what level of resolution do I need for the mesh if I want to resolve the chemistry?
The size of the fire itself on the cushion.
Or the thickness of the flame, if I want to resolve the chemistry. But I need to resolve the chemistry, no? So I'm stuck. I need soot. Yes, so the thickness of the flame becomes your domain, so you have to break it in a few hundred cells. So you're going to have a characteristic length scale for the chemistry. And that characteristic length scale for the chemistry is going to be much, 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 much smaller than the room. And this becomes your resolution. This is the mesh. So if you have a computational domain of the order of meters and a level of resolution of the order of microns, how expensive is that going to be? Oh, it's going to be pretty complicated, no? Now, what is going to be the characteristic length scale for radiation?
The absorption length in the exponential.
Yeah, the Beer-Lambert law. So basically, you have a decay, and you're going to have effectively an optical thickness.
Yeah.
Okay? Now, that optical thickness is going to be very different in the flame, it's going to be very different in the air, and it's going to be very different in the smoke. Okay? So the air, for example, is going to have a very, very low absorptivity. So it's going to have a very large optical thickness, so you can integrate over a long path length without error. Is that okay? So your Beer-Lambert law, and effectively you're going to have, in the Beer-Lambert law, you're going to have E kappa L. Okay? And your L can be very big because your kappa is constant. Okay? So the integration is actually one that is straightforward. But here you have stratified smoke with probably a higher density of soot in certain areas. You have localized soot in here, and you have the generation of soot in the flame, which is going to create soot volume fractions that are going to vary quite dramatically. And then your optical depth becomes very thin, and you have to start resolving it at a very, very narrow space. Also, how precise do you have to be with the temperature when effectively your radiation is sigma T to the 4th? Okay? So how precise do you have to resolve the temperature distribution? if you want to get it right, you have to shrink it. No? So you're going to have a characteristic length scale. You have the room. Now you have a characteristic length scale for radiation. And that characteristic length scale probably is actually going to go somewhere around here. But in some parts, it might be actually around here. And everything needs to be resolved. Okay, can you tell me, how are you going to compute this? Okay, Stephen Pope, do you know who Stephen Pope is? Okay, very famous professor from Cornell. He gave a keynote lecture, the hotel lecture in Warsaw. And he basically started by saying, you know, that the key to be able to do computation is to understand what you can simplify. Okay? And he said, for example, if you are dealing with certain parts of a turbine and you're interested in pollution, you actually create a simplification for the flow that gives you the strain, which is what you need, and you focus on your 257 steps of chemistry. Okay? If you have, in dealing with a car engine, for example, at the injection port, then the turbulence, the evolution of the turbulence is essential to be able to have, you know, things operating correctly, and then you might ignore the chemistry in that place and use a very simple chemistry, and then you are dealing with this flow that starts highly turbulent and then starts laminarizing itself at some point, and you need to be able to resolve that with a very dynamic type of model, okay, where turbulence is not a static variable, okay? And he said by doing that, he created a whole domain of different spaces in which he indicated, here we have this type of model, here we have this type of model, here we have this type of model. And he said it is impossible to pretend that you can do everything at the same time within a domain that cannot be ignored, because in fire, the boundary conditions are the fire itself. So you cannot extract one piece and ignore the boundary conditions, because the boundary conditions are what creates the fuel and creates the problem in the first place. The problem with fire is that you have everything at the same time. And this idea of separating different components of your model doesn't work at all, because they're all intertwined. And you have highly differentiated timescales, and they cover a range that is enormous, you know, from the nanosecond all the way to the minutes, because when you're talking about heating a solid, it's going to take minutes. So if you're going to heat the walls of this compartment, it's going to take several minutes. While if you're talking about your radiative heat transfer, you're going to be talking about nanoseconds, and you need to resolve the whole range. Now, in a similar way, the length scales, you go from the resolution of the flame all the way to the compartment. So again, you're going from meters to nanometers, okay? And the whole set of length scales needs to be resolved. You're going to go from areas of high chemistry activity that is essential to calculate the soot production to areas where there's absolutely no chemistry, where if your code is basically running chemistry everywhere, the computational cost becomes astronomical. Okay? So you have to find ways of suppressing that chemistry where you don't need it. Okay? And every component that I look is all tied up into one. So given that I hope we have agreed that I cannot do brute force computation here, it is not about me setting my Navier-Stokes equations, okay, setting my chemical kinetics equations, and then basically get the computer running. Because on the one hand, the complexity requires an extraordinary computational cost. But on the other hand, how do I justify doing that when these are the error bars of my boundary condition? And these are the error bars of what I need to compare these two. Is there a point to do this? Okay? Maybe in some very peculiar cases, but not in the reality of fires. Now, let me now say a hypothetical case, because of course, we always have an option, and there is a very popular one today that everybody uses, okay? AI. How do I AI this?
You get all the data on hundreds of fires, and you have your model trained on that.
Okay, so let me start with what data? So what is the data that you need? Yeah, but what do you need to measure?
Every parameter we can measure.
Yeah, because they all matter, no? So if I want to make sure that I get the soot volume fraction right with my trained algorithm, what measurements do I need? I need to measure soot volume fractions. Is that okay? Can I measure soot volume fractions at that scale with adequate precision? Okay? Temperatures. How am I going to, what kind of temperature resolution do I need if I want to AI my energy?
Maybe within 10 degrees.
And what level of density do I need when I have massive gradients of temperature all over the place and every single one of them has a dominant effect on an Arrhenius equation?
Well, of course, nobody can measure in the fires anyway.
Yeah, but how do we do that? How, I mean, am I going to use cars? Pleaf?
Laser-induced fluorescence.
At that scale and full of soot? With no symmetries of any kind? No, what I'm going to do is put 8 thermocouples. That's all I have. Okay.
Remembering to put in the radiation correction for the thermocouple.
Well, yeah, that's another story. Because they're going to get, basically their diameter is going to increase as a function of time because the soot accumulates on the bead, okay? So if I want to do my entrainment and I want to understand how much oxygen enters in the flame, I have to measure velocities. Am I going to do PIV? What kind of a laser do I need to get a laser sheet that basically has a height of 6 by 6 meters? Do any of you own a laser of that nature that can create a laser sheet of that dimension? You can't. So you know how we measure velocities in these things? We use this thing called bidirectional probes. Do you know what a bidirectional probe is? No, you wish. Basically what it is basically a little pipe, okay, that you put in the door, making the assumption that the flow is one-dimensional, okay, and you just put 2 pressure probes, and you measure the pressure in, pressure out, and with that you estimate the velocity component that goes in the direction of your tube. Because everything else that you put in there is going to burn down, it's going to get full of soot, and it's going to be a complete mess.
Hot wire anemometer with a tungsten wire won't work.
No, exactly. A hot wire anemometer will not work. So even the diagnostic techniques, the measurements that we have, are not amenable to train any algorithm. Okay? The only algorithm that can be trained to be able to deal with is the human brain. Okay? So you need to try to understand the physics, try to start simplifying the problem, and come up with something that is tractable. Not only has to be tractable and give you an answer, but that answer has to be consistent with the required precision, which actually is not very large because the uncertainty on all these things is negligible. Sorry, it's enormous. Is that okay? So in essence, if you think about this problem, the way you will think about most combustion problems, this is what you will need to do. Only to get to the point that you will realize that by the time you get started, you're going to get stuck here. Okay? Because just defining this heating profile and how the heat transfer is going to deal with the other thing already in itself becomes 2 PhDs. Okay? And that's the reality of the fire problem. So the fire problem is not about resolving every component of all the transport equations. Okay? The problem about fire is thinking, how do we combine things in a way such that we get the answer that we need? Is that okay? So let's take a 10-minute break, and then I'll show you a way in which we can do that. Okay?